What's up, guys? Welcome back to this series on reinforcement learning. In this video, we'll be introducing the idea of cue learning, which is a reinforcement learning technique used for learning the optimal policy in a Markov decision process. We'll illustrate how this technique works by introducing a game where a reinforcement learning agent tries to maximize its points. So let's get to it. Last time we left off talking about the fact that once we have our optimal cue function, Q star, we can determine the optimal policy by applying a reinforcement learning algorithm to find the action that maximizes Q star for each state. Cue learning is the first technique we'll discuss that can solve for the optimal policy in an MDP. The objective of cue learning is to find a policy that is optimal in the sense that the expected return over all successive time steps is the maximum achievable. So in other words, the goal of cue learning is to find the optimal policy by learning the optimal cue values for each state action pair. Let's now explore exactly how cue learning works. First, as a quick reminder, remember that the cue function for a given policy accepts a state and an action and returns the expected return from taking the given action in the given state and following the given policy thereafter. Also, remember this Bellman optimality equation for Q star we discussed last time? Go take a peek at the explanation we gave previously for this equation if you're a bit rusty on how to interpret it. It will become useful in just a moment. Alright, so back to the question at hand, how does cue learning work? Well, the cue learning algorithm iteratively updates the cue values for each state action pair using the Bellman equation until the cue function converges to the optimal cue function, Q star. This iterative approach is called value iteration. And to see exactly how this happens, let's set up an example appropriately called the lizard game. Suppose we have this environment. The agent in our environment is the lizard. The lizard wants to eat as many crickets as possible in the least amount of time without stumbling across a bird, which will itself eat the lizard. The lizard can move left, right, up, or down in the environment, and these are all the possible actions. The states are determined by the individual tiles and where the lizard is on the board at any given time. If the lizard lands on a tile that has 1 cricket, the reward is +1 point. Landing on an empty tile is -1 point. A tile with 5 crickets is +10 points and will end the episode. And lastly, a tile with a bird is -10 points and will also end the episode. Now, at the start of the game, the lizard has absolutely no idea of how good any given action is from any given state. It's not aware of anything besides the current state of the environment. In other words, it doesn't know from the start whether navigating left, right, up, or down will result in a positive reward or a negative reward. Alright, so therefore, the cue values for each state action pair will all be initialized to 0, since the lizard knows nothing about the environment at the start. Throughout the game, though, the cue values will be iteratively updated using value iteration. We'll be making use of a table called a cue table to store the cue values for each state action pair. The horizontal axis of the table represents the actions, and the vertical axis represents the states. So the dimensions of the table are the number of actions by the number of states. Since the lizard knows nothing about the environment or the expected rewards for any state action pair, all the cue values in the table are first initialized to 0. Over time, though, as the lizard plays several episodes of the game, the cue values produced for the state action pairs that the lizard experiences will be used to update the cue values stored in the cue table. As the cue table becomes updated, in later moves and later episodes, the lizard can look in the cue table and base its next action on the highest cue value for the current state. This will make more sense once we actually start playing the game and updating the table. Now, we'll set some standard number of episodes that we want the lizard to play. Let's say we want the lizard to play, 5 episodes. It's during these episodes that the learning process will take place. In each episode, the lizard starts out by choosing an action from the starting state based on the current cue values in the table. Specifically, the lizard chooses the action based on which action has the highest cue value in the cue table for the current state. But wait, that's kind of weird for the first actions in the first episode, right? because all the Q values are set to 0 at the start, so there's no way for the lizard to differentiate between them to discover which one's considered better. So, what action does it start with? To answer this question, we'll introduce the important trade-off between exploration and exploitation. This will help us understand not just how an agent takes its first actions, but how exactly it chooses actions in general. Exploration is the act of exploring the environment to find out information about it. Exploitation is the act of exploiting the information that's already known about the environment in order to maximize the return. The goal of an agent is to maximize the expected return, so you might think that we want our agent to use exploitation all the time and not worry about doing any exploration. This strategy, however, isn't quite right. Think of our game. If our lizard got to the single cricket before it got to the group of 5 crickets, then only making use of exploitation, going forward the lizard would just learn to exploit the information it knows about the location of the single cricket to get single incremental points infinitely. It would then also be losing single points infinitely just to back out of the tile before it can come back in to get the cricket again. If the lizard was able to explore the environment, however, it would have the opportunity to find the group of 5 crickets that would immediately win the game. If the lizard only explored the environment with no exploitation, though, then it would miss out on making use of known information that could help to maximize the return. Given this, we need a balance of both exploitation and exploration. So, how do we implement this strategy? To get this balance between exploitation and exploration, we use what's called an epsilon greedy strategy, and that's actually where we'll be picking up in the next video. There, we'll learn all about how an agent, the lizard in our case, chooses to either explore or exploit the environment. We'll continue with the lizard game there, so don't worry. In the meantime, why don't you come exploit the blog for this video, explore the Deep Lizard Hive Mind for exclusive perks and rewards, and leave a thumbs up to give us a signal that you're feeling good about your exploration of reinforcement learning so far. Thanks for contributing to Collective Intelligence, and I'll see you in the next one.
AlphaGo also uses reinforcement learning, not exactly in the same way. Here, it wasn't entirely built out of reinforcement learning, okay? Because for turn-based games, the algorithm for winning is actually quite easy. You just play all the moves to the end and then pick the ones that lead to positive outcomes. The only problem is that you can't compute that. There are too many of them. So you use what is called a value function. You unroll only a couple of moves, and then you use something that looks at the board and tells you this is good for white and good for black, or good for black. And that's what they built using reinforcement learning. And I find it interesting because it kind of emulates the way we humans solve this problem. This is a very visual game. We have a very powerful visual cortex when we look at the board. Go is a game of influence, and we see that in this region, black has a strong influence. In this region, white has a strong presence. So we can kind of process that. And what they built is a value function that does kind of the same thing and allows them to unroll the move to a much shallower depth. Because after just a couple of moves, their value function built using reinforcement learning tells them this is great for white or good for black.